Okay, so here we are in Unit 8. This is the last unit of 200A, and we are segueing into the world of statistics. Not really leaving behind the world of probability, what we've been studying all quarter, but changing our focus from learning an overall mathematical system for thinking about uncertainty and shifting now to questions involving working with data that we have and using that data to make inferences about things that we're interested in, things that we care about, things that we're researching, but can't observe directly. Okay. So we're going to start off with some basic definitions here of the key terms, and let's just get right down to it. Okay, so the first really important definition, the data that we're going to be talking about, we're going to be talking about a sample. Okay, so concretely, a sample is like a column in your spreadsheet. It's something that you've collected real concrete numbers on because you are interested in it. Um, from the point of view of thinking systematically about what we can learn from that, the way we're going to think about the data, all those numbers in your cells in the spreadsheet, is we're going to think about it as a collection of independent and identically distributed random variables. Okay, and we'll uh, use capital letters with indices x1, x2, xn. We might sometimes abbreviate that as a vector of random variables, bold x without a subscript there. Okay, so again, concretely, from your point of view, x1 might be your first observation, x2 is your second, n, capital N, is however many observations you collected uh, in your data set. They are concrete numbers. But what we are thinking, the way we are thinking about those numbers is that they're random draws from some underlying process that we don't quite understand, but we're going to use the observable data to make inferences about the theoretical concepts that we care about. So the key phrase in samples, and something that's going to be important going forward and understanding why we calculate the statistics we do, is this idea that all the x's are independent and identically distributed. That phrase is so important that you're going to see it abbreviated as IID. Okay, so in lots of methods classes, lectures begin with, assume you have a set of IID random variables x. So the idea here is that each of those x's is one realization of some kind of random variable. And here's the thing here's the kind of the shift in attitude that we have to make in going from probability to statistics. All throughout this quarter, we've been dealing with scenarios where we know something about the random variables. We know their distribution. Maybe we know the mean and the variance, or maybe we know the PMF. And that's probably struck some of you guys as kind of forced, and it should. It's very made up and hypothetical and not really the way we do things. Now we're thinking about observing the realization. So we see what happens at the end of this random process, and we try to use those realizations, use these observations on X to reason back, well, what can we learn about the PMF? What can we learn about the expected value of the process that's generating the data that we observe? Okay. Can we make inferences, for example, about the expected value of this unknown PMF? So as we go forward with statistical inference, we are losing the kind of hokey assumption that we know what the PMF is. We are still keeping the assumption that these X's are independent, and this identically distributed thing is really important. What it's saying is that each one of these X's is telling us something about the same underlying PMF. So it's telling us something about the same expected value. And so by observing many of them, we're getting much information about a single underlying process. So that's going to make our inference more valid. Okay, so the key thing with IID, let me just sort of emphasize something, is that they all the X's have the same mean or expected value. The same variance. That's what that IID business means, the identically distributed part of it. Fine, so that's a sample. What do we do with our sample? What do we do with our data? Well, we calculate statistics. And so statistic is just a function of that data. We have our sample, we have those real numbers that we as researchers have gathered. And we do something to them. Whatever we do is this G function. So in one sense, a statistic is a formula. It's something that you apply to your data. You've got a big column of numbers and you apply the formula and you get a single number that summarizes it, okay? And that is one important way to be thinking about a statistic all the time. So it's a formula we apply to data. The formula we're going to be looking at in the next video, might as well preview it here, is the we call the sample mean, sample average, people will call it. It's just take all those observations on X and calculate their average value. Add them all up and divide by N. Okay, so this is a formula. You know, you could type it into Excel at the end of the column. Take the average of cells A1 through A16, and you'll get the average of them. Okay, so it's a formula. But at the same time, we also want to be thinking about this other aspect of it. We want to be remembering that we're thinking about our data, even though they're numbers that we know, we are thinking about them as realizations of a random variable. So our statistic is a function of these random variables. Our statistic is a function of these X values that all come from the same random process. Okay, so that's the other thing to keep in mind here. So it is a function of the random variables, X1, X2, etc. And what this means is the statistic is itself a random variable, right? A function of a random variable is a random variable. And the distribution of the statistics, say G of X here, again, making a boldface X to denote that that's the vector of observations on X. So the distribution of the statistic comes from the distribution of the X sub i's. Okay. And so this process lets us calculate statistics from observable data to make inferences about unknown parameters. Sometimes people will say quantities of interest. That's kind of the jargony phrase there. Okay. So this is all sounding very abstract, and we're gonna start doing some examples now, but I wanna make a couple of more prefatory remarks about this abstract formula that is, in one sense, pretty weird, but in another sense, very helpful, okay? So what is weird about it is these X sub i's, I keep saying they're our data. They're the numbers that we know. Yet we are thinking about them as the random variables. These parameters, these unknown things, like the mean of this distribution that we don't know, we're thinking about that as fixed. So that's kind of out there. It's like if you guys read Plato's Republic when you were undergraduates, there's kind of this idea that there's some ideal form for everything. Like, so somewhere out in Plato's heaven, there's like the perfect cat, and all like real cats are just sort of reflections of this ideal form. That's kind of what these parameters are like. It is that weird of an idea. I am not really myself fully on board with that as a way of looking at the world, but it is totally useful for the basis of kind of classical statistical inference. And what we are doing here in Unit 8 is classical statistical inference. Okay, so we assume there is this, you know, kind of true unknown parameter out there, and what our data set is just doing is giving us these random realizations from these processes that we're trying to figure out, and we're using that data, we're collecting a lot of that data to get estimates of these things that are not random. The unknown parameters are not random, they're just unknown. Like I say, it's weird. Just bear with me, keep an open mind about it. You'll see it gets us to a place where we can do some very non-weird, common sense things with our data to reduce a whole spreadsheet of numbers that's too much information into a small set of numbers that are meaningful and communicate things that are empirically valid about the things that we care about. Okay, prefatory point number 1, check that off. Another way to think about this sort of like dual way of thinking about statistics, in one sense, it's just a formula that we apply to numbers. In another sense, it's a function of the random variables. When we think about statistics as a formula, that's telling us what we do. What do we do when we have a bunch of numbers and we want to summarize them? Well, typically we do calculate a simple average, okay? We apply this formula. That is what we do. Thinking about this sample mean as a function of random variables x1, x2, all the way to xn, that tells us why we do it. Why do we use this formula? And we're going to see in the next lesson why we use it, because it gives us an unbiased estimate of the underlying mean of the distribution that generates the x's. We're getting there in the next lesson. The final thing I want to say before we go to that next lesson and get a little more concrete with things, I want to make a comment about the uses of this word mean. We're going to start using this word a lot. And it has this weird relationship to other terms. Mean can be a synonym for expected value, right? We've used it that way. We've talked about, the expected value of the normal distribution is parameter mu, and we call it the mean, and it gets used interchangeably that way. Mean in the data statistics sense can also be used as a synonym for a simple average. Take a bunch of numbers, add them up, and divide by the number of numbers that you had, the number of things in your sum. So It could be synonyms for both an average, a formula that we apply to a set of numbers, and for expected values, an operation we perform on a random variable, are really not the same thing. Mean can be a synonym for both of those, but they're really not synonyms for each other. Okay, so you really would not say that this is the expected value of the sample. I think if you said it, people would probably know what you mean by it. Sorry, it's probably what you intend by it, what you're trying to say by it, but it would sound weird. And similarly, if you said, well, we're talking about a normal distribution with an average of 1, people would probably figure out that you meant mean in that sense, but it's not really right. It's not really the way people talk about it. The way to sort out this kind of complicated relationship that the word mean has to these other concepts, if we say sample mean always is sort of synonymous with an average. It means just taking the sum and dividing by n, an unweighted average, or where we're giving like equal weight to each of the observations. If we say expected value here, that could be synonymous with population mean. And so the metaphor here is that our sample is being drawn from a population, and it might be truly like we're taking a sample in an opinion polling sense from a broader population, but sometimes we're taking the sample from all the parallel universes that we could be observing here. So that population is kind of a metaphor, but when people say population mean, they are referring to something that is typically not observable. It is of theoretical interest, and it is the expected value of the process that generates the x's. So let me clarify one thing here. So all the x's are realizations of a random process. So there is that randomness. The parameters that characterize the PMF that gives rise to all of the x's, those are not random. Okay, so what we see are realizations from a process that has, again, in this world of classical statistical inference, some fixed expected value that we're trying to make inferences about. Okay, so that is kind of a long-winded theoretical setup. Let's go and see some things that are nice about the sample mean as a statistic, and I think you'll start to get a more concrete sense of what I'm talking about.